This is Lesson 22 in our Calculus 1 series, Antiderivatives. In this lesson, we're going backwards from taking derivatives. For a given function, we want to know whose derivative it is. So we start with this definition for an antiderivative. Capital F of x is an antiderivative of little f of x if capital F prime of x is equal to little f of x. So capital F is an antiderivative if its derivative is little f. So for example, f of x equals x squared is an antiderivative of little f of x equals 2x, because the derivative of x squared is 2x. But notice, x squared is not the only antiderivative of 2x. The derivative of x squared plus 5 is 2x. The derivative of x squared minus 1 is also 2x. In fact, the derivative of x squared plus any constant is equal to 2x. So when we talk about antiderivatives, we want to account for the entire family of functions that all have the same derivative. So we say that f of x equals x squared plus c is the general antiderivative of f of x equals 2x, where c represents any constant. And often we don't say the word general, we just say is the antiderivative. So if you're asked to find the antiderivative of f of x equals 2x, you're looking for the entire family of functions. You're looking for the general antiderivative. And so you add in the plus c at the end. So in this case, our antiderivative x squared plus c defines a family of infinitely many curves. So we want to know whose derivative is 2x. And our answer is y equals x squared plus c, where c represents any constant. So y equals x squared plus c gives us a family of parabolas. We have infinitely many parabolas that are shifted up and down the y-axis. And having the same derivative function of f of x equals 2x means that at any given x value, they all have the same slope. So notice at x equals 0, all of these parabolas have the same slope. They all have the same slope of 0. At x equals 1, again, they all have the same slope. They all have the same slope of 2. And so, as you could imagine, finding antiderivatives requires remembering a set of antiderivative rules. So based on the rules that we have for derivatives, we have the following rules for antiderivatives. If little f of x is equal to 1, then the antiderivative capital F of x is equal to x plus c. And that's because the derivative of x plus c is 1 plus 0. It's equal to 1. The antiderivative of x to the nth power is x to the n plus 1 over n plus 1 plus c. And this is true for n not equal to negative 1. We deal with the case when n equals negative 1 in Calc 2. The antiderivative of sine x is negative cosine x plus c. The antiderivative of cosine x is sine x plus c. The antiderivative of secant square x is tan x plus c. And the antiderivative of secant x tan x is secant x plus c. In all of these cases, we can take the derivative of capital F and we'll get back little f. That's how we're finding the antiderivative. Similar to when we take derivatives, we also have rules for the sum and difference of antiderivatives, as well as the constant multiple of an antiderivative. So if capital F and capital G are the antiderivatives of little f and little g respectively, then the antiderivative of f of x plus or minus g of x is going to be capital F of x plus or minus capital G of x plus c. Again, here I'm saying the antiderivative, so I'm talking about the general antiderivative, and I want to include here my constant. And we also have that the antiderivative of a constant times f of x is equal to that same constant times capital F of x, plus any constant. And again, keep in mind that when we're finding antiderivatives, we can always check our work by taking the derivative of our solution. So let's take a look at this example. F of x is equal to 1 minus x to the third plus 12x to the fifth. So let's find the antiderivative. The antiderivative of 1 is equal to x, because the derivative of x is equal to 1. The antiderivative of x to the third is x to the fourth over 4, because if we take our derivative here, the 4 will come down and cancel with this, and we'll have x to the third. The constant multiple of 12 will carry, and the antiderivative of x to the fifth is x to the sixth over 6. And then we have to add in our constant. So simplifying, we have a 12 and a 6 here, so that simplifies to 2, and so we have capital F of x is equal to x minus x to the fourth over 4 plus 2x to the sixth plus c. And as we just said, we could always check our antiderivatives by taking the derivative of our solution. So let's take our capital F and take its derivative. The derivative of x is 1. This is 1/4 x to the fourth, so I can pull out my 1/4. Then the 4 comes down, we have 4x to the third. Here I have a constant multiple of 2, and the 6 comes down, we have 6x to the fifth. And here the derivative of the constant c is 0. So simplifying, the 4 and the 1/4 cancel. The 2 times 6 is equal to 12, and we're here. And this is our original little f. Let's take a look at another example. Find the antiderivative. We have f of x equals 2 over x squared plus 5x. Now remember that when we learn to take derivatives, we would have to make sure that our function terms were in the proper form to fit our derivative rules. Well, the same thing's happening here with antiderivatives. I don't have a rule for a constant over x to a power. I only have a rule for a constant times x to a power. So I need to write this as 2 times x to the negative 2 before we can continue. Once we rewrite that, now we can take our antiderivative by using the antiderivative rules. The antiderivative of x to the nth power is x to the n plus 1 over n plus 1. So here we have 2 multiplied by x to the negative 1 over negative 1, plus this constant multiple of 5 carries down. This is x to the first power, so in the antiderivative we have x squared over 2. And then of course we add in our plus c. And so simplifying, we can pull this negative out front and take this x down to the denominator. We have negative 2 over x plus 5x squared over 2 plus c. And that is our antiderivative. And of course you can go back and check by taking the derivative. Let's take a look at another. Find the antiderivative. We have f of x equals radical x plus 3 over radical x. So just as in the last problem, we want to rewrite this before we attempt to use our antiderivative rules. We want to get it out of the radical notation. We also don't want to have any powers in the denominator. We want to rewrite this as 3 times x to a power. So here we have f of x is equal to x to the 1/2 plus 3x to the negative 1/2. Now we can take our antiderivative. We're going to add 1 to the power here. That gives us x to the 3/2 power, and then we divide by that number. Plus, the 3 carries down. We want to add 1 here, so we get x to the positive 1/2 and divide that by 1/2. And then add on our plus c. And so we simplify. Dividing by a fraction is the same as multiplying by its reciprocal, so this is 2x to the 3/2 over 3. This is 3 times 2 over 1, so that becomes a 6x to the 1/2, and plus c. And so this is our antiderivative. Let's take a look at another. Find the antiderivative of f of x equals 2 sine x plus cosine x. We know the antiderivative of sine x is negative cosine x, and so we have 2 times a negative cosine x, don't forget to use parentheses here, plus the antiderivative of cosine x is sine x, so we have plus sine x plus c. Simplifying, this is negative 2 cosine x plus sine x plus c. Now I'd like you to work on this problem. Find the antiderivative. F of x is equal to 2 minus 6x plus 6x squared minus 5 secant squared x. So please pause the video and use the antiderivative rules to find this antiderivative. The antiderivative of 2 is 2x. Remember, because the derivative of 2x is equal to 2. The antiderivative here is 6 times x squared over 2, so we have a minus 6x squared over 2. Here again our 6 comes down and we have x to the third over 3. And we know that the derivative of tan x is secant squared x. So here our antiderivative is going to be negative 5 tan x. And then we add on the plus c at the end. So simplifying, we have 2x minus 3x squared plus 2x to the third minus 5 tan x plus c. And that is our antiderivative. I hope you didn't get tricked by the first term here. Many times students forget that we're going in the opposite direction and they put a 0 here. But remember, we're taking an antiderivative. We want to know whose derivative is 2, and the answer to that is 2x plus any constant, but we group our constants together at the end here. Let's take a look at another. Find the antiderivative. F of x equals x squared multiplied by 2 plus radical x plus x to the third. Now, just as with derivatives, we can't just take the derivative of x squared and multiply it by the derivative of 2 plus radical x plus x to the third. We needed to use a product rule. Well, we don't yet have a rule for taking the antiderivative of a product of functions. So the only thing we can do here is first multiply out and then take our antiderivatives. So let's multiply out first. That's going to be 2x squared plus x to the 5 halves. Remember that we're adding exponents here, so we have 2 plus a half, that's 5 halves. And then plus x to the 5th. And so now that we've rewritten f of x, we can take its antiderivative. The constant multiple of 2 will carry, and we'll have x to the third over 3. Here we have x to the 5 halves, so we want to add 1 to that power, which gives us 7 halves. And so we have x to the 7 halves divided by 7 halves. And here, again, we add 1 to the power, so we have x to the 6th over 6, plus c. And of course, we want to simplify, which means we want to take this 7 halves in the denominator and instead write it as 2/7. And so we're here. We have 2/3 x to the third plus 2/7 x to the 7 halves plus 1/6 x to the 6th plus a constant. Let's take a look at the next one. Now we're doing the same thing here, but the notation is a little bit different. Now we're saying f prime of x is 3 secant x tan x plus x. Find the original function f of x. So it's the same thing here. We're taking the antiderivative. But instead of calling this one little f and this one capital F, now we're calling this f prime and this f. But again, the process is just the same. So whose derivative is secant x tan x? We know that's the derivative of secant x. So our antiderivative here is going to be 3 secant x plus, this is x to the first, so our antiderivative will be x squared over 2, and then we have a plus c. And that's our antiderivative. Now let's take a look at what we have here. We're given a second derivative and we're asked to find the original function. So we're going to have to antidifferentiate twice. Starting with f double prime, we take the antiderivative and that will give us f prime. So let's do that. Here we have a negative cosine x, the negative carries, and then the antiderivative of cosine x is sine x. Here the constant multiple of 7 carries. We have x to the 3 halves. We want to add 1 to that power. That becomes x to the 5 halves, and we divide by 5 halves. Here we have a constant of 5, so whose derivative is 5? That's 5x. And then we add on our constant at the end, so plus c. And then we'll just simplify this. Dividing by 5 halves is the same as multiplying by 2/5. So we have f prime of x is equal to negative sine x plus 14/5 x to the 5 halves plus 5x plus c. So this is a representation for f prime. And notice it's a family of functions because we have a constant here. But we were asked to find f. So let's take another antiderivative. The antiderivative of negative sine x is equal to cosine x. Here our 14/5 carries, and we have x to the 5 halves, so we want to add 1 to that power. We get x to the 7 halves over 7 halves, plus the constant multiple of 5 carries. Here we have x to the first, so we have x to the second over 2, plus, this is a constant, so whose derivative is c? C times x. So our antiderivative for this term is c times x. And then we have to add in another constant. So I'm going to call that d. So here is a representation for our original function f. So let's just simplify here. This is 14 over 5 multiplied by 2 over 7. That gives us a 4/5. And so we're here. Now notice above that we were finding general antiderivatives. And so we had these constants hanging around. Every time we take an antiderivative, we introduce a constant. But now let's find particular antiderivatives. So let's go back to the original example. We had little f of x is equal to 2x, and we said the general antiderivative is capital F of x equals x squared plus c. Now I want to find the particular antiderivative of f of x equals 2x with capital F of 1 equals 5. So now I'm saying from this entire family of solutions of the form f of x equals x squared plus c, I want the one that goes through this point, that goes through the point 1, 5. So how can we do that? We start with our general antiderivative, capital F of x equals x squared plus c, and we know that f of 1 must equal 5, so we plug in x equals 1 here, we get 1 squared plus c, and we set that equal to 5. That allows us to solve for c. So in this case, c must equal 4, and capital F of x equals x squared plus 4 is the particular antiderivative that we're looking for. It's the antiderivative of f of x equals 2x with f of 1 equals 5. So notice when we have this extra condition here, this is a point that the original goes through, that specifies for us which one of the family of solutions we're looking for. So the general antiderivative of f of x equals 2x is capital F of x equals x squared plus c. That gave us infinitely many parabolas in the plane. We want the particular one that has capital F of 1 equaling 5. So we want the particular parabola that goes through this point. And so we found that the equation for this parabola is capital F of x equals x squared plus 4. So that's a particular solution. It's a particular antiderivative. Let's take a look at another. Find f of x. F prime of x is equal to negative 2 sine x plus secant square x, and we're given f of pi is equal to negative 1. Now they're not using the word particular here, they're not saying find the particular antiderivative, but it's understood that that's what we're looking for because they're giving us a point that our antiderivative goes through. So we're not looking for a whole family of curves here, we're just looking for the particular one that goes through this point. So please pause the video and work on that. Here our negative 2 carries as a constant multiple. The antiderivative of sine x is negative cosine x. And we know the antiderivative of secant square x is tan x. So we have negative 2 times negative cosine x plus tan x plus a constant. Simplifying, that becomes 2 cosine x plus tan x plus c. This is the general antiderivative, but we want the particular one that has f of pi equals negative 1. So this is our function f of x. We plug in f of pi, and we set that equal to negative 1. We know that cosine of pi is negative 1, tan of pi is 0. So this says negative 2 plus c is equal to negative 1. And so that says c must equal 1. Now, what were we asked for here? We're asked to find f of x. So let's make sure we answer the question. Let's take that c value of 1 and plug it in to our formula for f of x. And so f of x is equal to 2 cosine x plus tan x plus 1. And that's our solution. I often see students forget to take that last step and plug that c value into the original function. So just be sure you answer the question and do that. Let's take a look at another. Find f of x. Now we're given a formula for f double prime of x, and we're given a point that f prime goes through and a point that f goes through. So now you're going to do the same thing that we just did, but you're going to do it in 2 steps. You're going to go from f double prime to f prime using this evaluation of the derivative, and then take that result and take the antiderivative to get to f and use this point. So you should end up with a particular solution for f of x. one function, not a family of functions. So please pause the video and work on that. So we start by finding f prime of x, and so we want to take our antiderivative from f double prime. So this constant multiple of -2/9 will carry. We want to add 1 to the power here, so that's going to give us x to the -2/3, and so we divide by -2/3, plus this constant of 4 is going to carry here, and then here we have x to the -7/3. We want to add 1 to that power, so we get x to the -4/3, and we divide by that. And then we add on our c, our constant. So first let's simplify here. This is a -2/9 multiplied by a -3/2. And this is a 4 multiplied by a -3/4. And so we're here. We have 1/3 x to the -2/3 minus 3x to the -4/3 plus c. And so writing that without negative exponents, we're here. Now what do we know about f prime? We know that f prime of 27 is equal to -1/3. So that allows us to find this constant c. So f prime of 27 is going to be 1 over 3 times 27 to the 2/3 minus 3 over 27 to the 4/3 plus a constant. And we know that that must equal -1/3. So we set it equal to -1/3. 27 to the 1/3 is 3, so square that, we get 9. So this is 1 over 3 times 9. Again, 27 to the 1/3 is 3. Take that to the 4th power, we get 81. So this is minus 3 over 81, which simplifies to 1 over 27. And so here we have c must equal -1/3. So we go back and plug that into our formula for f prime. And so f prime of x is equal to 1 over 3x to the 2/3 minus 3 over x to the 4/3 minus 1/3. And now because we want to take another antiderivative, I'm going to write this again with negative exponents so we can compute our antiderivative. F of x is going to be 1/3. We want to add 1 to the power here. That gives us x to the 1/3 over 1/3 minus 3 times. We have x to the -4/3 here. We want to add 1 to that power, so we have x to the -1/3 again over -1/3. The antiderivative here of 1/3 is 1/3 x. And then we have another constant, so I'm going to call that d. So simplifying here, we get x to the 1/3 plus 9x to the -1/3 minus 1/3 x plus d. And writing that without a negative exponent, we're here. Now we're almost through. We want to use the fact that we know f of 27 is equal to 0 to solve for this constant d and find a particular solution for f of x. So we plug in x equals 27 here, and we set that equal to 0. And so we get d must equal 3. So let's go back here and plug d equals 3 into our formula for f of x. And this is our solution. Now recall that for a distance function s of t, the velocity v of t is equal to s prime of t, and the acceleration a of t is the derivative of velocity, so that's v prime of t or s double prime of t. Now, using the methods above, we can start with an acceleration, go back and find a velocity function, go back again, find a distance function. So using the methods above, for objects moving with a constant acceleration, if we know the initial velocity and initial position, we can find the distance s at any time. So let's take a look at this example. A penny is dropped from the observation deck of the Empire State Building, which is 1,250 feet above ground. Find the height of the penny above ground level at any time t. What is the velocity of the penny when it hits the ground? And if the penny was thrown downward with a velocity of 16 feet per second, how long would it take to reach the ground? Okay, so what do we have here? A penny is dropped from the observation deck of the Empire State Building. So when an object is dropped, we know that the only governing force on it is gravity, because we're neglecting air resistance. So we know that gravity provides a constant acceleration on the penny of -32 feet per second squared. And this is the only force governing the movement. So we have our acceleration function, a of t is equal to -32. So right away, we can write down a form of our velocity function by taking an antiderivative. That's going to be -32t plus a constant. Okay, well, what do we know about the velocity? What's the velocity at time 0? Our penny is dropped, so there's no velocity at time 0. That velocity is 0. So we plug 0 into the velocity function and then set that equal to 0. That tells us this constant is equal to 0, and so our velocity function is v of t equals negative 32t. Well, once we know that, we can write down a form for our distance function, the height of the penny above ground at any time, by taking the antiderivative here. So we're going to have negative 32 times t squared over 2 plus another constant. This simplifies to negative 16 t squared plus a constant. Okay, well, what do we know about the height of this penny? We know that at time 0, the height is 1,250. So we plug 0 into our function for s, and we set that equal to 1250. That tells us our constant d must equal 1250. And so our function for height of the penny at any time is given by s of t is equal to negative 16 t squared plus 1250. This is the solution to part A. Now in part B, we're asked what is the velocity of the penny when it hits the ground. So the first thing we have to do is find the time, the t value for when it hits the ground, and then plug that into our velocity function. So how can we find the time value when the penny hits the ground? Well, what's the height when the penny hits the ground? The height is going to be 0. So we set s of t equal to 0, and we solve for t. So t squared is equal to 1250 over 16, or 625 over 8. And so t is equal to 25 over 2 radical 2. And we're going to use this exact t value when we plug into the velocity function, but just to give you an idea, that's 8.8 seconds. So plugging that into the velocity function, we have negative 32 times that t value. And so that comes out to negative 200 radical 2 feet per second, which is approximately negative 282.8 feet per second. So that's the velocity at the time when the penny hits the ground. So don't drop any pennies off the Empire State Building. Now, part C, if the penny was thrown downward with a velocity of 16 feet per second, how long would it take to reach the ground? So now, instead of being dropped, there's going to be an initial velocity here. So the velocity at time 0 is going to be negative 16 feet per second. This is thrown downward, so that's a negative velocity, negative 16 feet per second. That changes v of 0. So now we have v of 0 equals negative 16 feet per second. That tells us our v of t is going to be negative 32t minus 16, because it was negative 32t plus a constant c, and plugging in t equals 0, we have to get negative 16. So we have our negative 16 as our constant here. So what does it say about our distance function? Our height function is going to be s of t equals negative 16t squared, now minus 16t plus a constant. So I'm going to call this d2. And again, we know that s of 0 equals 1,250, so we set that equal to s of 0. And so this constant is equal to 1250. And so now our function for height looks like this. And at what time does the penny reach the ground? Again, that happens when this height is equal to 0. So let's set that equal to 0 and solve for t. So using the quadratic formula, we get 16 plus or minus 8 radical 1254 over negative 32. And we know that we need to have a positive t value, so that means our numerator is going to have to be negative, and that means we're going to have to subtract here. And so this is approximately 8.4 seconds. And just keep in mind, this time should be faster than the time we had above when the penny was just dropped, because now the penny was thrown downward, and it is in fact faster. We had 8.8 seconds above, and now we have 8.4 seconds approximately. Let's take a look at another example. A car is traveling at 60 miles per hour when the brakes are applied, giving a constant deceleration of 15 feet per second squared. How far does the car travel before coming to a stop? So notice that deceleration means the acceleration is negative. So you know that your acceleration here is negative 15 feet per second square. And we're asked how far does the car travel before coming to a stop. So we're looking for the distance here at the time when the velocity is 0. So using the methods that we saw above, please pause the video and work on that. So again, we're asked to find s of t, the distance, at the time when the velocity is equal to 0. And what are we given? Well, we're given that our acceleration is negative 15 feet per second squared. So right away we know that we can find a form for the velocity by taking the antiderivative. That's going to be negative 15t plus a constant. And we're given an initial velocity of the car because the car is traveling at 60 miles per hour. So at time equals 0, when we start to apply the deceleration, the brakes, the velocity of the car is 60 miles per hour. But notice we're in feet per second square here, and this is in miles per hour. We need to do a conversion. So we need v of 0 in terms of feet per second. So we have 60 miles per hour. We know there's 5,280 feet in 1 mile, and you should memorize that just in case. We know that there's 3,600 seconds in 1 hour. So just remember that when you're doing your conversions, you want to get your units to cancel. I don't want my miles to end up in my final answer, so I want them to cancel. So I have miles on top here. That means I need miles in the bottom here, and feet on top. I have hours in the denominator here. That means I need an hour on top, seconds in the denominator. So when we simplify, we have a 60 here. That'll leave us a 60 here. We have hours that cancel with hours. We have miles that cancel with miles. And we get 5280 over 60 feet per second, which simplifies to 88 feet per second. So now we have our initial velocity in terms of feet per second, and now we can proceed. We know that when t is equal to 0, our velocity is going to be 88. So let's plug t equals 0 and set this velocity equal to 88. That tells us our constant c must equal 88, and this is our velocity function in feet per second. What are we asked for? We're asked for the distance traveled at the time when the velocity is 0. So we need to set this equal to 0 and solve for t. And so we get t is equal to 88 over 15 seconds, which is approximately 5.9 seconds. But again, for our computations, we'll use the exact 88 over 15. And so we are looking for the distance at this time, which means we need s of t. So here's v of t. How do we get s of t? We take an antiderivative. So we have negative 15t squared over 2 plus 88t plus a constant. Now how can we find this constant? What information do we have about the distance function? Well, we could think about measuring distance from the point at which the brakes were applied. So at time 0, we can say that the distance traveled was 0 at that time. And we can use s of 0 equals 0. And so that says our constant d here is equal to 0. And so our distance function is s of t equals negative 15t squared over 2 plus 88t. This is how far the car has traveled t seconds after the brakes were applied. And we want to know how far the car traveled over this time, over the 88 over 15 seconds. So we're going to plug that into our original function. And so we get 7744 over 30 feet, which is approximately 258.1 feet. So just as finding derivatives required remembering a bunch of derivative rules and knowing how to apply them, so does finding antiderivatives. And in the rest of this semester for Calc 1, we're going to just do some basic antiderivatives, and then we spend most of the semester of Calc 2 finding antiderivatives using more advanced techniques. And this concludes our lesson on antiderivatives.